All right. So our operating system of the day, we have finally reached Mac OS. I don't know, yay, maybe not yay. I'm going to be honest with you, I hate them all, so. All right, so Mac OS, you know who this is made by because most of you have used it at some point in your life. Made by Apple, obviously. It's not some kind of joint collaboration with Microsoft, believe me. The two don't like each other, nor have they ever really. It was released in 1984, and there's actually two distinct releases of macOS. There's the classic one, which many of you may not have used, and then there's the one that we're all using today if you're using any kind of Mac product, and that's Mac OS X. And there's a pretty big difference between these two. So the classic one, that was up to 2001. And what's interesting with it is in the very earliest versions of it, in order to actually give the user a better user experience, to give them better performance, they actually had the operating system partially stored on a ROM chip. It's a read-only memory chip. So that's kind of interesting because they didn't actually need to have a hard drive in the machine, and they didn't have to boot it by loading it off of a too slow disk into RAM and then so on and so forth. It was actually right embedded on the hardware, so it's going to be super, super fast loading times and so on. Now what's interesting is at this point in time, you know that Unix and all these other operating systems offered you things like concurrency and virtual memory and networking and security and all those modern features that we have become accustomed to. But if you look at the earliest versions of macOS, you find that a lot of those things are actually missing because they didn't really feel that the consumer needed that. So there wasn't support for multiprocessing up until about 87. And even then, it was kind of iffy. And in 1991, the form of concurrency they actually supported was cooperative concurrency, not preemptive concurrency. So cooperative concurrency, just to refresh your memory, because you know you got exams coming up in like a few weeks. Cooperative concurrency is we only actually do a context switch. Excuse me. Excuse me. You only do a context switch when there is a thread terminating, or a thread blocking, or a thread voluntarily yielding. That's why it's called cooperative, because you have to cooperate with each other, and if you don't cooperate, there's no concurrency. And that is what macOS used from 1991 and on. And by the way, they're not the only ones. Windows did the exact same thing. They also didn't even have virtual memory until 1991. I would point out virtual memory is not new. Virtual memory has been around since the mid to late 1950s. And here we are in 1991 and Apple is just bringing it in. Why can they get away with this? Because consumers in the 80s and 90s didn't really know what computers were for. I know my friends who had old Apple IIs, they were like, oh look, I can play Wheel of Fortune on it. The thought of like surfing the internet didn't occur to people, or multitasking or anything like that, so they could get away with it. Now, they realized that this particular operating system wasn't going to cut it in the future, and so they were going to have to build a new one. And they had an option. They could build one from scratch, or they could buy one from somewhere else. And Apple, like so many others, chose to do the buy one from somewhere else option. And they actually acquired a company called Next Step, well, maybe that's not the name of the company, the name of the OS, but they acquired it, which is actually a variant of BSD. And Mac OS X is a very heavily modified next step, which means Mac OS X is actually a very, very heavily modified version of BSD. So if you open like a terminal in Mac and you're like, oh, look, it's Bash. I guess the new one they like to push is like ZSH or something, but I still use Bash. And it's got LS, and it's got CD and all those things, all these Unix commands. It has them because it's still BSD somewhere underneath all of that Mac pixel art. There's still BSD there. So because they got BSD from this, they automatically got preemption, and they automatically got protected memory, and all of those wonderful things that Unix and BSD had had for like decades beforehand. And that's the version that you are using today. Now, one other thing that they did is Mac's file system, originally called HFS. People don't really like this file system, and originally HFS, HFS+, they actually kept it from the classic version and brought it up to Mac OS X. And a lot of people don't really like it because it was not case sensitive. And when I think it was High Sierra came out, Mac actually released a new file system, which I think is called APFS, and it's for SSDs only, which means it has optimizations that are specific to how SSDs operate. And APFS actually moved to a case-sensitive file name system. And that caused a whole bunch of havoc because if you had older software that was expecting things to not be case-sensitive and all of a sudden they became case-sensitive, that's a problem. But it's nice to see that Apple's moving into, the 20th century. All right, a lot of people like to make fun of them for not using case-sensitive file names. So, one thing I want to show you, which is really interesting. So when we look at Windows, I'll bring you back to this idea. But one thing Apple has done really, really well over the decades that they've had their operating system is they've been consistent about the look and feel. So even if we go back to the very first version of Mac OS, I bet you know how to use it. I know there's no colors, and I know it's only like 320 by I think 240 pixels, but and some of the elements that you use are probably missing, but it still looks roughly the same as what you use today. Still got the menu in the top, still got the Apple icon in the upper left corner, still roughly the same thing. Now if we go to one of the later ones in the classic version, colors now, right? And now some of the other elements that we're familiar with are starting to actually appear. Yes, I know that is Exploder running in Mac OS. There was a period of time where Microsoft thought, hey, we should release our applications for Mac so that we can, maybe make more money or something. Okay. And I don't need to show you the one from today because most of you have it sitting in front of you or you have seen it at some point in your life. But you know that it's just this with a little bit cleaner graphics, a little bit smoother. They have maintained a really solid, consistent look and feel. And when we look at Windows, you're going to see that there's no such thing as consistency. None of them look alike. None of them even behave the same. All right. So, how today is going to go. No, don't worry, you're not learning about link layer today. That's my other course. Okay. So just a couple announcements before we get started. Don't forget that you have a quiz again on Friday. Pretty much, so you'll have one this Friday, you'll have, I think, one next Friday, and then I think you have one on the last day of classes, whatever the schedule says, I don't quite remember. The next quiz is going to be on devices. So devices and device drivers. The other thing I wanted to mention is now that A2B is out of the way, it's A3 time. So that is mostly what we're going to be doing today is talking about assignment A3. Has anyone gotten started? Are you done? No. Not yet. Had to ask, right? Okay, and after we're done with the assignment 3 stuff, if we have time, I have a review handout for the devices section, and then maybe we'll get time to start our new topic, which is file systems. So to start with then, let's look at lovely assignment 3. And actually, I wanted to do one thing before I show you the actual assignment. And that is, I want to take you to the course website. So if you're sitting there and you're panicked because you don't still have A2A working, or you don't have A2B working, I want to calm you down before we look at what A3 involves. What I'm going to do is I'm going to show you the A3 marking report, because these are all of the tests that we run on A3. You will note that only 2 of these tests look familiar to you. One of them is wide fork, and the other one is hog party. None of the other tests use any process management calls or argument passing. So if you do not have A2A working, you only have to worry about wide fork and hog party. And if you don't have argument passing working from A to B, relax, you don't need it for A3. Totally not needed, because the only one we're doing is hog party. So if you did not finish the last 2 assignments, you would only lose 5 out of 50 marks, potentially. So my recommendation to you is to, if you are in that boat, seriously consider reverting to your assignment 1 code. If you haven't even finished A2A, revert to your A1 code and build A3 on top of that. Because you will spend too much time trying to fix those previous broken assignments than focus on getting new marks for this new assignment. And that's totally fine if you don't pass 1 or 2 tests here. And if it's just argument passing that you don't have working, don't even bother fixing it. As long as hog party works in your assignment, none of these tests use argument passing. So you can take a deep breath. All right. So then, what is magical assignment 3? When we were talking about virtual memory, we actually kept coming back and telling you how OS 161 did things. Or more than often than not, it was how OS 161 didn't do things. Because OS 161's implementation of virtual memory is actually really bad. So bad that they called it dumb virtual memory. For example, when you freeze something in OS 161, when you call kfree, nothing happens. There is absolutely no memory management. They have a magical pointer that says, this is the address of the next free chunk of memory. And every time you call kmalloc, guess what happens? It just takes it from that pointer and advances it. And when you call kfree, nothing happens. It doesn't give any memory back at all. Yeah, you're going to fix that now. Some other things is that if your TLB is full, OS 161 kernel panics and dies. Obviously, that does not make sense. If a cache is full, you are supposed to, choose a victim, kick them out, so that you can actually push someone back in. So you're going to fix that one as well. Another interesting quirk of OS 161's virtual memory is that it doesn't understand that the text or code segment should be read-only. And so user programs in OS 161 can overwrite constants and can overwrite their code segment. That's fun. Also pretty bad. You get to fix that one as well. And at the very end, so after fixing the TLB and fixing the read-only memory and adding memory management in, there's one last thing. As we discovered in our virtual memory section, OS 161 actually uses segmentation for virtual memory. And you should remember that segmentation introduces external fragmentation, which can be problematic. So we want you to fix that. We want you to actually combine paging with segmentation to get rid of the fragmentation problem. And then you'll have virtual memory that behaves a little bit better. Now, some of you might be panicking. This sounds really hard. I think if you were to search the UW Reddit, people are always having discussions about which is the hardest 350 assignment. And they mostly will tell you most people have a hard time with 2A and 2B. 3 isn't hard. There are some elements which may be particularly challenging for you, but there's some things you don't need to deal with anymore. You're not going to be testing, all of our tests don't use like 300 threads. It's a little bit more straightforward, I find, to actually implement this assignment. So a lot of people actually have an easier time with A3 than the previous 2. You might be different. You're welcome to go on the Reddit page and search for it if you want. Don't look up other people's solutions though, okay? All right, so the first thing that you need to do, and this is actually the easiest part of the whole assignment, you can do it right now, and you can pass the very first test, and that is to fix the TLB problem. So right now, our TLB, if it is full, panic and die. What we want you to be able to do is when the TLB is full, we want you to choose a victim and evict them, and then insert the new TLB entry. We are not, however, asking you to implement any of these cache eviction strategies, so we're not going to ask you to implement the clock algorithm. We're not going to ask you to implement optimal, because of course you can't actually do that, because you don't know the future. We're not going to ask you to implement any cache eviction algorithm. They're already implemented for you. All you need to do is call it. It's like 1 or 2 lines of code. It goes in VM fault, which is why I said you could literally do this right now. We want you to use TLB random. It is going to choose a random victim in the TLB, evict them, and replace them with the new TLB entry. It does all of that in one function call. So all you need to do is stop it from panicking when it's full, and instead call our good friend TLB random. And there you go. You're done the first part of the assignment. It's not so bad, right? Now you might be wondering, well, isn't random like the worst possible cache eviction strategy? Actually, no. There have been a fair number of studies that show that random is actually a half-decent way of doing it. And if you want to know more about that, there's some guys in engineering who actually do their entire research careers based on cache evictions and cache implementations. And they have wonderful papers over there about that. All right, part 1 of the assignment, right? You can do it right now. Nobody gets out their laptop. No. You're waiting to the 12 hours before the deadline. I know. I get it. All right, so after you have fixed the TLB problem, the next thing that you should fix is the read-only memory problem. So what we know is that when you actually read in the ELF file, that's the binary file for the program, it actually does identify the fact that the text segment should be read-only. It's just that the operating system doesn't actually have any mechanism for recording the fact that it's read-only and telling the TLB and the MMU that it should be treating that as read-only as well. So what you need to do is you need to, on a VM fault, so when you actually throw that exception, when you determine that the fault address is in the text or the code segment, that's the first one, you need to set a flag that says, hey, this is a read-only address. And then later on in VM fault, when you're adding that TLB entry to the TLB, you need to set the read-only flag. And look, we've even given you the line of code to do it. It's right here. You're going to have to add the flag yourself, but I presume you know how to add a boolean or an int or a char, or maybe you decide to do a flag with a double. I don't know, that's weird, but you can do whatever you want. I don't care. Wow, that's easy, right? Okay, not quite. So this is part one of making read-only memory work, but it's not enough. Because if you do this, then when the program is actually loading itself into the address space, on the very first attempt to write the very first piece of memory into the address space, you haven't even run the program yet, this is just during the loading of the address space part, the MMU is going to throw an exception that says you are trying to write to read-only memory. And then you can be like, oh, that's interesting. What it means is that you can't actually set that segment to be read-only until it's loaded. Because you actually need to be able to write to it in order to load the segment in the first place. So what you need to do is add another flag. And where you want to add this flag is into your address space structure. And what that flag should be is to indicate, have I loaded the address space or not? And it should start out as false. And then at the very end of load elf, which is responsible for loading the address space, you set that flag to true. And then in VM fault, you set the read-only flag if the address space is loaded, which you will know from the flag in the address space structure, and this is a code segment address. Now, it's not quite enough. We need one more tiny detail. So here's the problem. When you are loading the address space into memory, you're going to be creating a bunch of TLB entries. And because the same process is running, we're not actually going to clear the TLB out when we actually start running things, which means that if I load my address space and all my TLB entries from loading indicate that the code segment is read-write, and then I immediately run the program, then it's also going to think that that segment is read-write because the TLB entries, which were already there, say so. So that would be bad. So there's one other thing you need to do at the end of load elf. You need to clear the TLB. And remember that the function that you need in order to clear out the TLB is that horribly named function asActivate. So you're going to set the flag to indicate that, hey, it's I've done loading the address space, and then you clear the TLB with asActivate. And at that point, read-only memory would work. But we still kind of have a bit of a problem. If I'm a user program in Windows and I try to write to a constant, does Windows blue screen of death and die? Linux doesn't kernel panic and die when this happens. So maybe OS 161 shouldn't either, and that's the last bit of the read-only memory problem. Is when a user program tries to write to read-only memory, it will cause the operating system to panic and die. The operating system didn't do anything wrong. So maybe we shouldn't be doing that. So the last thing that you need to do is detect when we are trying to write to read-only memory in a user program, and instead of causing the operating system to panic and die, you need to kill the process. Now, what you need to do this is have VM fault return an appropriate error code or signal. And that will actually get picked up when MIPS trap calls kill cur thread. And then you need to modify kill cur thread to see your signal, I tried to write to read-only memory. And then inside of kill cur thread, that's where instead of panicking, you want to kill the process. Now, there's three different ways you can do this. You can add all the code to kill the process right inside of kill cur thread. That's not very good programming design. Maybe don't do that. You could write a function that is very similar to sysexit called syskill or systerminate, which does roughly the same thing as sysexit, except its exit status and exit code would be different, because that process is not terminating from a call to exit. It's terminating because it did a bad thing. Different exit code. So you can write your own function to do that. Or another option that I've seen many students take is they take their existing sysexit and then modify it so that it now has a parameterized exit status. So now you can call sysexit from kill cur thread and pass it that I was signaled to die, I was told to die, and if you're calling sysexit from syscall, you pass it wexit. How you do it, we don't care. Just make it work. The point is, when you run the test that does try to write to read-only memory, the operating system shouldn't panic and die, the program should die, and nothing else. All right, any question about that stuff so far? Okay, so that's the two easy parts of the assignment. And surprisingly, those two parts there actually don't take a lot of code to implement. It's something where it's probably going to take most of you about an hour to do both of those parts. And now we move into the more complicated part of the assignment, which is actually implementing memory management. Now here's the thing, the operating system is actually responsible for managing all of the system's resources. So access to the CPU, access to each of the individual devices. It's also responsible for managing how much memory is actually available. When you open a new program and you ask for an address space, it's the operating system who has to go to physical memory and actually find you some memory. The OS is supposed to be managing that, and right now it doesn't. So we have some physical memory here. And during the bootstrap process, we use this function called ram stealmem, which is going to take, this is the pointer for where free memory is, and it's going to literally take memory from that pointer and advance it. So ram stealmem is going to do. It's going to physically take some memory that never gets given back. We do that for the bootstrap process. It starts at address 0. Don't change that. That needs to stay that way. What we want is for after that bootstrapping process, after that memory has been stolen, we want you to manage what's left. So how do you do that? Well, we want to use paging. Because actually the MMU, even though OS 161 is using segmentation, the MMU in OS 161 is actually doing paging. So what we want to do is when we allocate stuff with alloc k pages and free k pages, the denomination that we are actually doling out memory in is whole pages. So we need to manage the remaining memory as pages. So what we're going to do is we need to logically divide the memory that is left into pages. And then we need to keep track of which of those pages are free and which ones are not. And we do this in a structure called a core map. So I'm going to turn the lights on and draw a sample of a core map here. Let's move that a bit. So let's do core map version 0.1. Okay, so for each frame, I need to know, is it in use or not? So I'm going to have the frame number, and I'm going to keep track of it's in use or not. So I've got frame 1, 2, 3, 4, so on and so forth. And then if it's in use, we'll set it to be 1, and if it's not in use, we'll set that entry to be 0. So now you'll notice I kind of have alluded to the fact that there might be more columns here. When you free memory, do you tell it how much memory to free? You pass it an address, and magically, free knows exactly how much memory to free. Do you know how it knows? Core map. When we do a contiguous allocation of memory, that is multiple pages at a time, we indicate that that is a part of a contiguous allocation. So this is page whatever of some number. So this is 1 of 2, and this is 2 of 2. And this is 1 of 2, and this is 2 of 2, and this is 1 of 1, and so on. Now when I call free, and I pass the address, the starting address, I'll be like, oh, I'm calling free on this one here. And oh, look, it's a part of the contiguous allocation. And so my free will know to not only free this one, it'll know to go to the next one as well and free it too. And it knows that because of the core map storing that information. So what's going to happen now is when you allocate memory, you are going to go to the core map and you're going to search for some number of contiguous pages. You are going to mark them as now being in use, and then you'll set the page of how many to mark it as being a part of a contiguous allocation. And when you are freeing, you find that entry in the table, and you free all those entries that correspond to the contiguous allocation. Now you have memory management. Now, looking at this here, you can imagine that we're going to have one of these entries for every single possible page of memory that we're trying to manage, which means that there is the potential for there to be millions of them. Millions of entries with 1, 2, 3, 4 integers. That's going to take up a lot of space. So something you need to be very cautious about when you are creating the core map is how much space are you actually using for that core map. Because whatever memory you are using for the core map cannot be used for anything else, ever. And one of the things that we are going to be doing in our testing of your implementations is instead of giving you more memory, we are giving you less. That's how we're going to check and see whether you're able to actually free anything, because we're going to take so much memory away from you that if free doesn't work, the OS will panic and die because it ran out of RAM. So if you use too much memory for your core map, you won't actually have enough left over to do anything else. And it's now at this last assignment where if you haven't been calling k-free in fork or anything else, you might want to go back and fix that. And if you've got some giant process table of like 1,000 entries, you might want to go back and change it to like 32. If you've got an array of process ID numbers and it's like 10,000 long, you might want to go back and make that smaller because we are really going to be restricting your memory use here. Now, there is actually another way that you can implement this core map where you only need to store an integer for each. So instead of doing 4 things for each entry, I only need 1. So I'm going to translate this core map here to my core map, which is a lot simpler. Done. That's it. As it turns out, you don't need all that crap over there. If my core map entry is a 0, it means it is not in use. If the core map entry is not a 0, it means it is in use. And what we're going to do is we're going to start here and we look and we say, oh, it's a 1, it's in use. Should I look forward and see if this is a part of the contiguous entry? So you mark this one as free, and then you go to the next entry. And if the value of the next entry is whatever you were plus 1, then it's a part of the same contiguous allocation. And if it's equal to you, then it is not a part of you. Now, the only thing that you need to do, in addition to storing an integer for each, is you also need to store the address of the start frame. Because you need to be able to actually convert the index here into the actual address of the proper frame. But that's significantly less memory. I'm not going to tell you any more details about it. There are a few more little nitpicky details. I can tell you, however, that that will be about the smallest amount of memory you can use for this. Now, can you do something else? Yes, and I don't care what it is you do, just make it work. I do not advise creating a struct. I also, when you're creating your core map, please don't call malloc. You're implementing it. So it kind of doesn't make sense. Here's the other thing. We're at the point where the operating system is booting up, which means all of RAM belongs to us. That means when you're creating your core map, there's no point in you calling kmalloc to ask for memory, because it all is yours. So what you're going to do to create the core map is calculate an address and write to it. Do not call malloc. Calculate the address and write to it. Now, how do you know how much memory you have available to you? There is a function called RAM get size. It is going to return to you the low address and the high address of the available memory to you after bootstrap. After the bootstrap process, you must never call RAM steal mem again. So keep that in mind. So to find out how much memory you actually have available, you call RAM get size. It's going to return to you the low and the high address, from which you're going to have to do some math to figure out how much memory that actually is. Then you're going to have to logically divide that into pages. And there's one critical thing that you also need to know. The frame numbers and the page numbers must be divisible by the page size. So I cannot have a frame number or a frame address that starts at 500. That doesn't work. It must be divisible by the page size. So after you have figured out how many entries you need to have in your core map, and you've calculated the amount of space you need for your core map, the place that you should put the core map is immediately following the area that we've allocated for the bootstrap process. Another critical thing, the core map should not be tracking the memory used by the core map. The core map should only have entries for the memory that follows it. I see a lot of people with nasty, nasty bugs on assignment 3 that comes down to they accidentally are tracking the core map inside the core map. And they do not have a very fun time. It is not a bug that shows up in any meaningful way. So make sure that your core map is only tracking things that follow it. And make sure that your pages and frames are actually page aligned as well. So you're going to have to use some rounding and all that fun stuff all over again. Now you might be asking yourself, when do I free the core map? Well, you could free it when you shut the operating system down. It needs to be alive for the entire time the OS is alive. But if you're shutting the OS down, you don't have to free it. Because you're dead. You don't care. So don't worry about freeing it. Okay, some other things about this. there are parts of the operating system that are going to be calling kmalloc before your core map is created. You need to create a flag in the operating system to let the world know whether the core map exists yet or not. Before the core map exists, you need to use the original RAM steal mem. After the core map has been created, you must use the core map from that point onward. Where should you be looking at creating this core map? You need to be taking a close look at the function VM bootstrap, which I'm sure you can find. All right. So now that you've got your core map, and unfortunately this is not something that's fairly easy to test, but once you've got it, which is why I really recommend you write the old map on paper and make sure it works out first before you write the code. Now you actually need to go back and modify alloc and free to actually use your core map, because right now they don't. So you need to look at alloc k pages. Alloc k pages is going to allocate a contiguous block of pages. So if you call alloc k pages 7, then it's going to give you 7 contiguous pages. Now it needs, once the core map has been created, we want 7 contiguous pages from the core map. Now, you're going to be very tempted to modify alloc k pages to talk to the core map directly. I am going to advise that you don't. Look at a function called getPages. That is where you want to put the code to get things from your core map. There is already some code in that function. It still needs to live there, but the code that is there is only useful for before the core map is created. So leave that there for pre-core map, and then add the part for post-core map. Why am I recommending that you modify getPages instead of allocKpages? Because unfortunately in OS 161 they weren't so consistent on which function they called to allocate memory. And parts of the address space structure call getPages directly instead of allocKpages. So you've either got to modify them to call allocKpages, or you could just put all this in getPages, which is what most people do anyways. You can do whatever you want. I'm just, so you know in advance, there's this funny quirk. Now free kpages, that is when you're going to want to modify. Because what you're going to do now is, well, now you actually have to fill the function in because it doesn't really do anything. You're going to need to search through your core map, find that contiguous entry, and mark all of them as free that are part of that contiguous entry so that they can be reused. There you go. You now have memory management. You can now get all of the tests to pass for assignment 3. The last part of the assignment, we actually don't have any tests for. Yeah. We're aware, obviously. So it is entirely possible you get up to the slide done and 100% of the tests pass. And you think, why the hell would I do the last part of the assignment? I passed all the tests. Well, we know about this, and we are going to look at your code this time. Not for style. Because believe me, no programmer likes any other programmer style. It's like looking at a demon, it's like, evil code. Everybody else's code is ugly except yours, right? What we are looking for is we are going to look to see if you implemented the last part of the assignment. There will be some very clear modifications that you'll have to make in order to implement the very last part of the assignment. And if we don't see them, then we will know that you didn't even try. And if you do not try, you lose 5 marks. It doesn't mean the assignment is now at a 45. It means if you got 50 out of 50 on the tests, then now your score is 45. And if you got 30 out of 50 on the tests and you didn't do the last part, your score is now 25. It is a 5-mark penalty if you don't do the last part. Yes, this is why I would say at least 50% of the class does not do the last part of the assignments, because it's a lot of code and there's not really much benefit, except, like studying and stuff. I don't care what you do. It's not hard to implement the last part. This isn't the last part, by the way. I appreciate the fact that you're probably in 341 right now, and you might be in 370, and maybe you decided to take 360 as well, and maybe Stat 231. I don't know. You've got other courses. I appreciate that. I'm not going to judge you for not doing this last part. I like to be very upfront and honest about it. You can pass all tests without it. So what is the last part then? Page tables. So right now, OS 161 is doing contiguous allocations for each of its segments. That causes fragmentation. What we want you to do is combine paging with segmentation. And how we want you to do it is actually a very popular, very common way of doing it. What you're going to do is, instead of having a multi-level page table or a single page table for the whole address space, this is cool. You're going to have one page table for each segment. Now, why is that cool? It is cool because if you have a page table for each segment, you only have to store the page table entries that are valid. Because you know the size of the segment. The segment is contiguous in virtual memory. Because of that, you know exactly how many pages there are. So you only need one page table entry for each of them. We don't need a page table entry for every possible page. Just the ones we are using, and we know exactly which ones those are. So our page tables are actually quite efficient, because they are only storing exactly the things we need to know and nothing else. So you don't need to store a valid bit or anything like that. But you are going to need 3 page tables. You will need one page table for the text, the code segment. You need one page table for the data segment and one for the stack segment. Which means if we are looking at the address space structure, you need to replace the physical address elements for each of these segments with a page table. Because now, instead of just keeping track of the relocation, you actually need to keep track of which physical frame each of those virtual pages actually maps to. All right. Now, in order to do this, as I said, this is probably the most code that you actually have to modify for the whole assignment. Because you actually have to modify pretty much all of the address space functions, and you even have to modify VM fault. So after you've modified the address space structure, you need to go into AS_create, because AS_create is where we initialize the address space structure. You might need to allocate something in there. Or maybe not, but definitely you're going to want to do that in AS_define region. In AS_define region, this is actually where we are defining the size of that region. So we're saying this region is 12 pages. Well, once you know that the region is 12 pages, now you know how much memory you're going to need for that segment's page table. It was 12 pages. So you need to allocate a page table that fits 12 page table entries. You will do that in AS_define region. And now you actually have the page tables. They are currently empty, however. Now I know there's this bit in here that says optionally set the read-write permissions for each segment. Don't bother, because you've already handled that in the first part of the assignment. So I would recommend just ignoring that part. It's not useful. All right. In AS_prepare_load, this is where we are actually allocating the physical memory for the segment, and we are actually going to be loading that segment into the address space structure. The act of actually loading the address space segment into the address space is where you will actually need to start populating that page table you just created. You're going to need to allocate a frame for each and every page of the address space, and as you allocate each frame, you're going to need to update the page table. Right now, it calls allocate pages n. Actually, I think it calls gets p pages n. But that's going to give you a contiguous allocation. You don't want a contiguous allocation. You want to scatter these to the wind. And so what you're going to do is, instead of calling it one big allocation, you're going to replace that one call with a for loop of calls for individual allocations. So you're going to go from something like allocate pages 7 to for I equals 1 to 7, allocate pages 1. And when you do that, you go from having one contiguous block to the potential to have them scattered. Now, most of the time they're going to be contiguous, but they don't have to be. And now you've filled in your page tables. Then we have to go and look at ASCopy. Remember, ASCopy creates a new address space, and then it's going to copy the old address space into the new address space. Well, when we actually copy the old address space into the new address space, we have to actually update the new page table as well. So you're probably going to need to make a few changes to ASCopy. And in ASDestroy, you're also going to have to make a lot of changes. Because not only do you, instead of calling free once for each segment, now you actually have to call free on each and every single page of each segment. So what you're going to do is go through the page table for each of those segments and free each page separately. And then don't forget at the very end to actually free the page tables themselves. So there's a lot of stuff that you're going to have to add to that. Now, something that's not in here, because we go straight to this one page here, is once you get using your page tables, the address translation done in VM fault when there's a TLB miss doesn't work anymore. And you're going to have to replace the existing address translation with a page table lookup. I'm going to figure that one out. And if you're wondering, how do I assign page numbers to things? I don't care. Give them your favorite letters, spell words, do it incrementally. You are assigning your page numbers now. All right. Now, a couple things. Just to remember is that anything that is below user stack, which is that 8 address there, that is for the user, and that is going to be going through the TLB. Anything that is greater than or equal to that value is a kernel address. But those are both going to be virtual addresses. You should never be using physical addresses. And this is a big mistake I see in assignment 3 every single term, is people calculate this in terms of the physical address, and then they try to write to the physical address. Well, here's the problem. The MMU tries to translate every single address. So you pass it a pre-translated address, and the MMU doesn't know that. So the MMU then translates it, and you get a TLP miss or some other wacky error. So make sure you do not read or write from physical addresses directly. You need to actually convert them to the appropriate virtual address before you do the read or write to it. There are macros within the operating system to actually do that. There's like KV, ADDR to P, AVDDR. There's a whole bunch of them. You can look them up and make your own, whatever you want. Just pay attention to that. Do not read or write a physical address. You will have a very, very, very bad time. All right. Any questions about assignment 3? So one last thing about testing, then. Up until now, you have been told we do not run tests back to back. That is no longer true. Because with this assignment, you're fixing memory management, which means tests can now be run back to back. And we will be running tests back to back. So we will be running things like add back to back. It's not add, sort. We will be running it back to back like 10 or 20 times. So when you're doing your testing, make sure that you are testing things running back to back 30 times. And if you can run it back to back 30 times, you're probably good. One other thing to note is that we are only running on a single CPU now. So you do not have to do 2, 3, 4, 8 CPUs. Just one. That's going to make things a lot simpler. All right. Anything? Any questions? All right. Yeah?
Do you know how much memory to look at?
I think if you look in the A3 hints, it actually tells you how much memory you get for each test. Now, some tests we run multiple times, and the first time we'll give you a lot of memory, and the second time to test for one particular thing, and the second time we give you a small amount of memory to test for a separate thing. But if you look in the A3 hints, I think it tells you. We don't really hide much, to be honest. All right. Yep. Is this posted on Getty? Yeah, this is posted on Getty. And then when I get home tonight, I will post the video on YouTube as well as, well, it's already on Twitch right now, but yeah, I'll post it to YouTube so that you can all do your assignments while listening to someone tell you exactly how to write the code. Actually, it's making our anti-cheating software a little bit complicated because it's like everybody, if you follow exactly what I said, and like the videos are getting watched like 500 times, so it's like, how do I tell the difference between you just doing exactly what I told you to do and you copying off each other? Whatever, I don't care. There. All right. Anything else? All right. With that then, I'd like to do a brief review because, you know, your final exam is coming up in a few weeks. Of the last topic that we were covering. And I want to bring up some formulas here, so just give me a second. I did not mean to unzip that. So we were talking last about devices. And in particular, we did a lot of discussion about how hard drives work. And I know that's probably seen as very dated by many of you, but people still use them. People still use magnetic tape. It's still relevant. So what I have for you then is a lovely problem. It's not one of my favorites. It's not my absolute favorite. You'll get my absolute favorite one in a few days. It's nobody else's favorite, but. So what this is we have a single disk and a CPU, and the disk is there's a program that's going to do some amount of computation followed by a disk I/O operation. And while we are doing a disk I/O operation, well, we want to know what the CPU utilization is going to be. So if there's only one job, only one thread running, then obviously when we're doing our I/O operation, the CPU sits idle. But now, in the second part, we're going to introduce another thread. So we'll pass this around. Take the next, 8 minutes. See how far you get on it. My recommendation to you is before you attempt to figure out the CPU utilization, you really need to calculate how long does this I/O operation actually take to go. And then you do the CPU utilization. And formulas, which I will post my formula guide for this on Piazza a little bit later.
Oh, wait,
We can use the same. Well, that's be a little more obvious.
In your request to say this time, that seat is in 5 minutes.
So the latency is n, so that average would be 5 milliseconds, I think, which is 100 seconds, which is 10 milliseconds per rotation. So now there's 100 rotations per second, and then there are 10 milliseconds per rotation, which is 10 milliseconds times 100 is 1 second. Yeah. So that's the max. Latency is 5 also. So the cost time for 1 second is going to be 10 milliseconds. Divided by
All right. So looking at this problem here, there are 2 parts to it. Really, the first part, before you can even look at the CPU utilization, is you need to compute how much time does it actually take to service this I/O request. Now, from the information given, you'll notice it says block instead of sector. Just use the sector math with the word block. It will become more apparent when we talk about file systems as to why that's okay. For now, just take my word for it. You'll see why that is in a bit. So to start out with, the first thing that we want to do is let's compute the cost of a full rotation. So for a full rotation, it is 10 milliseconds. And when we're doing the I/O service request time, because we actually haven't specified the current position and the position we need to go to, we're going to use the average rotational latency in our service request time. So 1 full rotation is 10 milliseconds, but our average rotational latency is going to be 5 milliseconds. Then we get the seek time is 5 milliseconds. Now, you can use that straight up and just assume when they say the seek time is 5 milliseconds, they mean that is the average seek time. So our seek time is given at 5 milliseconds. And now we need to actually compute how long does it take to actually transfer 1 block of data. Well, in order to do that, we need to figure out how many blocks actually fit on a track. So we start by looking at the the capacity of each track. So we're going to do the track capacity is the disk size divided by the number of tracks. So this is going to be 2 to the 27 divided by 2 to the 10. So that means we should have 2 to the power of 17 tracks. Or, sorry, not tracks, bytes per track. So now I need to figure out how many blocks actually fit into this track, because I need to know what percentage of a rotation do I need to do to actually read that block. So the number of blocks per track is the capacity of the track, which is 2 to the 17, divided by the capacity of block, which is 2 to the 12, which gives me 2 to the 5, which you should all know is 32. So there are 32 blocks for each track. Now I know that I am going to read one of those blocks, which means my transfer time is 1 over 32 times the maximum rotational latency, which is 10 milliseconds. This is going to give you something that looks roughly like 0.3 milliseconds. On an exam, you're welcome to leave it in fractional form. That's totally fine. Then the cost of my IO service request is the sum. So it is 5 millisecond rotational latency plus the 5 millisecond seek plus the 0.3 millisecond transfer time. So you should get something that looks roughly like 10.3 milliseconds. Or whatever fraction you left it in. I had a calculator, so yeah.
So like the seek doesn't happen at the same time as the rotation?
Remember that the disk never stops rotating. So as we are actually moving the read-write head, the disk is still rotating. When it gets to the beginning of its sector, if we are not in the right spot, we don't stop, which means we have to keep going until, yeah. So we kind of treat them separately. All right, so this is the first part. The next part is looking at the CPU utilization. So I am going to erase this in 1 second. So if you want this information, take a picture now, or watch the video, I guess. Hey, that's convenient. All right, so then we know our service request time is 10.3 milliseconds. And in the first part, it says that there's one thread, and that thread does 5 milliseconds of compute followed by an IO operation, and it does it forever. So if we draw out the timeline for that, what we see is that we do 5 units of compute, 10.3 of IO. 5 units of compute, 10.3 IO. And this continues forever. Since there are no other threads, and the CPU is not involved in the data transfer, not involved in this, that means that whenever this IO operation is happening, the CPU is sitting idle because we have to wait for the IO operation to stop. So, and there's nobody else to use the CPU. So the utilization for the first one, there's our repeating block. So the denominator is 15.3 and the numerator is 5. So you end up with a utilization of about a third. It's not bad. And now let's see what happens when we introduce the second thread to the mix. So for the second thread, here we've got thread 0. Now it does its compute and then it does its I/O. When it's doing its I/O, the CPU is free, and so the second thread can do its compute. But it can't start its I/O. You cannot have 2 I/O operations on the disk at the same time. You cannot physically be in 2 places at the same time. I cannot be here and laying in my bed fast asleep at the same time, as much as that would be nice. So this thread has to wait for the disk to become available. And so it's just going to have this wait here. And then once this I/O operation in thread 0 is done, now thread 1 can do its I/O operation. And while that's going on, thread 0 can do its compute. And then they're actually going to take turns using the disk like this. Now, to calculate the utilization here, we see that the repeating unit is actually the I/O. And so our denominator in this case is the service request time, and the numerator being the compute time. So you get roughly a 50% utilization. Now, you want some practice for the final exam? Try this with 3 threads. What utilization do you get with 3 threads? And if you're like a super, super excited person and you just love things like math and 341 so much, come back and tell me, is it possible to ever get 100% utilization out of this? And if it is, how many threads do you need for it? And if you can't get 100% utilization, what is the maximum you can get? I don't know the answer off the top of my head, because I just made this up. But that's good review. So next class will be file systems.